For the purposes of this discussion, let's separate out the functions of programs that might be running on the system. One set of programs are those that are part of the operating system. Typically, they are memory resident and perform services on behalf of other work or manage resources. From this, we will make the simplifying assumption that if there is no work to run, then these programs will have nothing to do. Therefore, work or application programs are going to be represented as those things that people want to have done. So if someone is logged on and wishes to execute a command or perform a function or run a program, then each of these would be considered work. Work might also be automatically scheduled to run at various times, but the point here is that it is something that needs to be done by an individual. Application programs also have the general characteristic of being specifically started and stopped. If we use a PC as an example, we're going to consider all those processes that are running in the background in support of the operating system as being part of Windows or Unix. However, when we invoke a particular program like Word or Excel, then we are running work that is running because we have elected to start it, as well as choosing when we terminate it. Since programs need access to the processor to run their instructions, they are represented internally as one of two types. One type, which is the most typical, is called the TCB, or Task Control Block. This is the name of the internal structure or control block used by z/OS to identify such work, so we use the same acronym to reference the work itself. As a result, when we run something in an address space, we have a TCB that identifies the actual program or programs that are being run under the control of this task. Another type of structure is the SRB, or Service Request Block, which represents short-running work of high priority that is normally used by authorized programs to signal events or the completion of requests. Generally, SRBs do not reflect general work because there are several restrictions that apply to the kinds of things that they can do. We refer to these two types as dispatchable work because each is capable of being dispatched to run on a physical processor. Since we are only interested in an overview, we can see that the way the system is structured is that when work comes into the system, it results in an address space being created, which represents where the work will live while it is running. A TCB is created to represent the program being run, as well as any programs that it may call. An address space may have more than one TCB in it. In this slide, we can see the address spaces highlighted in different colors, each representing the virtual storage available for that job. In addition, we can see TCBs indicated within these address spaces, representing the programs running there. z/OS uses these TCBs to reflect all the work that is running, and a TCB may be ready to run, or it may be waiting for some request to complete. There could be multiple TCBs that are created by a unit of work. Since they each represent a unit of work that can run, it is possible to increase the level of parallelism for work by having multiple TCBs that all represent different things that can occur simultaneously. As an example, let's consider a database system. When a query comes in for data, then the database software can create a new TCB to handle the query. That way, the main task can continue to wait for other queries. As they arrive, new TCBs can be created to handle these requests, providing a degree of parallelism where multiple requests can be processed and independently compete for access to the processor. In that way, other requests don't have to wait simply because the database task is processing a single query. When an existing task creates a new TCB, this is referred to as a subtask. So we have a parent task which can create daughter subtasks. When the subtask ends or fails, control is automatically returned to the parent task. This mechanism is extended farther for batch work by having another started task called an initiator. The initiator examines input queues for work that is ready to run. If it finds something, it brings it into the system and creates a subtask representing this new unit of work. When the work completes, or if it abnormally terminates, the initiator gets control back, processes the termination, cleans up the address space of memory that has not been freed, and looks for new work to run. In this way, there is a continuous turnover of new work that can run as long as there is an initiator available. In this slide, we see a screen capture displaying all of the tasks that are running within the address space that represents my TSO user ID. Each of these performs specific functions, and as can be seen on this display, they are all in a wait state, waiting for me to enter a command. What each of these tasks specifically represents is outside the scope of what we want to examine, but basically there are several things that we can see on this slide. First, we can identify the TCBs that exist, as well as the programs that they represent. We can also see the information that indicates where this control information is located in RAM memory. So if we were engaged in debugging a problem, we could use this information to look into memory to see what status information or conditions are currently in effect. If we look under the column labeled Module, we will see the first three module names which represent the system tasks that always run in this address space. The TCBs that represent my session begin with the module name called IKJEFT01. In the ZOS environment, TCBs are also assigned a priority, which is used to determine their position on the dispatcher's queue. The higher the priority, the higher in the dispatch queue a unit of work is. The dispatcher is invoked every time an interrupt occurs on the processor, so the highest priority ready task is always given a chance to run. What this means is that low priority work can be significantly delayed if there are large amounts of higher priority work in the system. The only way a low priority unit of work can run is when all higher priority tasks are waiting for something. From this we can see that the busier the system is, the more likely it is that low priority work will be delayed. Let's now shift over to examining I/O processing.